The early 20th century witnessed groundbreaking discoveries in physics. Scientists were puzzled by atomic and subatomic behavior. Classical physics could not explain these phenomena. This led to the birth of quantum mechanics. Quantum mechanics began with the study of particles. It aimed to describe their behavior at the smallest scales. These initial discoveries set the stage for a new understanding of the universe. The journey from particles to fields began here. The shift from classical to quantum physics was revolutionary. Traditional theories failed to explain certain experimental results. This opened doors to new theories and models. The quest to unravel atomic mysteries led to profound changes in physics. Quantum mechanics has since evolved. It has reshaped our understanding of reality. From particles to fields, this journey has been captivating. Let us delve deeper into this fascinating evolution. The concept of particles has ancient roots. Early scientists like Democritus spoke of indivisible atoms. However, it wasn't until the 20th century that particles were truly understood. Quantum mechanics provided a new lens to observe these tiny entities. Particles were initially thought of as small, solid objects. They could not be divided further. This view was challenged by quantum discoveries. Scientists realized that particles behave differently at microscopic scales. The double-slit experiment played a crucial role. It showed that particles like electrons exhibited wave-like properties. This was contrary to the classical view. The experiment hinted at the dual nature of particles. Quantum mechanics sought to explain this duality. It introduced new concepts and mathematical tools. Scientists began to see particles not just as objects, but as entities with wave-like characteristics. This marked the beginning of a paradigm shift. Particles and fields represent two different concepts in physics. Particles are discrete, localized entities. They occupy specific positions in space. Fields, on the other hand, are continuous and spread out. A particle can be thought of as a small point. It has mass and charge. Fields, such as the electromagnetic field, permeate space. They can influence particles within their reach. Understanding fields requires a shift in perspective. Instead of focusing on individual particles, one considers the space around them. Fields describe how forces are transmitted across space. They provide a more comprehensive view of interactions. This distinction is crucial in quantum mechanics. Early theories focused on particles. However, to fully understand interactions, scientists had to incorporate fields. This led to the development of quantum field theory. Fields offer a richer framework for understanding nature. They bridge the gap between particles and forces. This dual approach has proven essential in modern physics. It has opened new avenues for exploration and discovery. Max Planck was a key figure in the birth of quantum mechanics. In 1900, he introduced the concept of quantization. He proposed that energy is emitted in discrete units, or quanta. This idea challenged classical physics. Planck's work began with blackbody radiation. Classical theories could not explain the observed spectrum. Planck suggested that energy levels were quantized. This revolutionary idea laid the foundation for quantum theory. Planck's constant became a fundamental quantity in physics. It represents the smallest possible unit of energy. His work paved the way for future discoveries. It was the first step towards understanding the quantum world. Planck's contributions were monumental. They marked a shift from classical to quantum thinking. His ideas inspired a new generation of physicists. The journey from particles to fields began with his groundbreaking work. Section 5. Albert Einstein, Bridging the Gap with Light. Albert Einstein made significant contributions to quantum mechanics. In 1905, he proposed the idea of light quanta, or photons. This was part of his explanation for the photoelectric effect. Einstein's work bridged the gap between particles and waves. He suggested that light could behave as both a wave and a particle. This dual nature was a radical concept. It challenged the classical wave theory of light. His work earned him the Nobel Prize in Physics in 1921. Einstein's contributions extended beyond light. He introduced the concept of wave-particle duality. This idea became a cornerstone of quantum mechanics. It influenced many subsequent theories and experiments. Einstein's insights were profound. They helped shape the development of quantum theory. His work demonstrated the need to rethink traditional physics. It opened new doors for understanding the quantum world. Section 6. Niels Bohr and the Quantum Leap. Niels Bohr was another pivotal figure in quantum mechanics. He developed the Bohr model of the atom. This model introduced the idea of quantized energy levels. Electrons could only occupy certain orbits around the nucleus. Bohr's model explained the stability of atoms. It accounted for the spectral lines of hydrogen. This was a significant achievement. His work bridged classical and quantum ideas. Bohr's contributions extended beyond his atomic model. He introduced the principle of complementarity. This principle states that particles can exhibit both wave and particle characteristics. It depends on how they are observed. Bohr's ideas were revolutionary. They provided a deeper understanding of atomic structure. His work laid the groundwork for future quantum theories. The transition from particles to fields was influenced by his contributions. Section 7. Erwin Schrödinger and the wave function. Erwin Schrödinger made a significant impact on quantum mechanics. He introduced the concept of the wave function. This mathematical function describes the probability of finding a particle in a given space. It became a central element of quantum theory. Schrödinger's wave equation revolutionized physics. It provided a new way to understand particle behavior. The equation could predict the behavior of particles over time. This was a major breakthrough. The wave function brought a new perspective to quantum mechanics. It suggested that particles could exist in multiple states simultaneously. This idea challenged classical notions of determinism. Schrödinger's contributions were profound. His wave equation became a cornerstone of quantum theory. It bridged the gap between particles and fields. The wave function remains a fundamental concept in modern physics. Section 8. Transition from particle theories to field theories. The shift from particle theories to field theories was a major development. Early quantum mechanics focused on particles. However, to fully understand interactions, scientists needed a new approach. This led to the development of quantum field theory. Quantum field theory describes particles as excitations in fields. It combines quantum mechanics with special relativity. This unified approach provides a more comprehensive understanding of nature. The transition to field theory was driven by experimental evidence. Particle collisions and interactions required a new framework. Field theory offered a solution. It could explain complex phenomena that particle theories could not. Field theory has become essential in modern physics. It underpins much of our understanding of fundamental interactions. The journey from particles to fields has transformed our view of the universe. It remains a vibrant area of research and discovery. Section 9. Quantum field theory, a new paradigm. Quantum field theory, or QFT, represents a new paradigm in physics. It merges quantum mechanics with field theory. This approach provides a unified framework for understanding particles and forces. QFT describes particles as excitations in fields. These fields permeate space and time. The theory can explain complex interactions, such as particle creation and annihilation. It offers a deeper understanding of fundamental forces. QFT has led to many important discoveries. It has provided insights into particle physics and cosmology. The theory has been instrumental in the development of the Standard Model. This model describes the fundamental particles and their interactions. QFT continues to be a vibrant field of research. It has profound implications for our understanding of the universe. The transition from particles to fields has opened new frontiers in physics. QFT remains at the cutting edge of scientific exploration. Section 10. Importance of the wave function in quantum mechanics. The wave function is a central concept in quantum mechanics. It describes the probability of finding a particle in a given state. This mathematical function is essential for understanding quantum behavior. The wave function provides a new perspective on reality. It suggests that particles can exist in multiple states simultaneously. This idea challenges classical notions of determinism. The wave function introduces an element of uncertainty. The wave function has many important applications. It is used to predict the behavior of particles in various situations. It plays a key role in quantum computing and quantum cryptography. The wave function is fundamental to modern quantum theory. Understanding the wave function is crucial for studying quantum mechanics. It provides a deeper insight into the behavior of particles. The concept has transformed our view of the universe. The wave function remains a cornerstone of quantum theory. Section 11. The impact of quantum field theory on modern physics. Quantum field theory, or QFT, has had a profound impact on modern physics. It has transformed our understanding of particles and forces. QFT provides a unified framework for describing fundamental interactions. QFT has led to many important discoveries. It has been instrumental in the development of the Standard Model. This model describes the fundamental particles and their interactions. QFT has provided insights into particle physics and cosmology. The impact of QFT extends beyond particle physics. It has applications in condensed matter physics and quantum computing. QFT has also influenced the development of new technologies. It continues to be a vibrant area of research. The development of QFT marks a significant milestone in the evolution of physics. It represents a shift from particle theories to field theories. QFT has opened new frontiers in scientific exploration. It remains at the cutting edge of modern physics.